Hey, Math 1. We are going to do the notes for Section 6.2, Chapter 6, Section 2. Continue solving systems of equations. We're going to learn a new method today. So here we go. So you can see today that our goal is to solve a system of linear equations by what's called the substitution method. Boom, right? And I want to remind you, and you do not need to write this down, just listen. In the first section of the chapter, we learned to solve a system of equations by what we call the graphing method, right? And you don't need to write this down, but that was when you took your two equations and you graphed them. So maybe one of them made a line that looked like that, maybe one of them made a line that looked like that. And what we learned is that all the solutions to an equation are on its line. So the point where the lines cross, that would be the solution to the system of equations. Like for this, it might be x equals -3, y equals 1. Or we could write that as an ordered pair, right? You could write it as x equals y equals, or you could write it as an ordered pair. All right, so today we're going to learn a new method to solve a system, to find an x and a y value. And this time we're going to use algebra to solve the system. Specifically, we're going to use what's called the substitution method, right? So these are the directions to the substitution method, and they will make more sense as I do it. Now, each of these examples has a little twist to it that's different, so make sure you listen to each one and fill them out. So the best time to use the substitution method is when one of the equations can be easily solved for one of its variables. And I might even go a step further and say the best time to use the substitution method is when a variable is by itself. I think that's the best time to use the substitution method. But I'll show you how this works. So there are kind of 4 steps, and I'm not going to read them. I'm going to come back and point them out as I do them. All right, so step 1 we're going to do first, and that is get a variable by itself. Solve one of the equations. So we're going to look at example 1. And step 1 is to get a variable by itself. And ideally, you pick the easiest variable to get by itself. That would be a variable whose coefficient is 1, or it doesn't really look like it has a coefficient. So I'm going to get this variable by itself, the y in the second equation. I like to draw a little line down the middle between the two equations to separate them. And then here I would add 2x to both sides. And when I do that, the y is now by itself. That is step 1. Step 1 is to solve one of the equations for one of its variables. That just means get a variable by itself. All right, here comes the big step. Step 2 is the big step. It is to substitute that amount, the amount we just got here, into the other equation in place of the variable you solve for. Let me show you that. So I'm going to take what y equals. Y is equal to -3 plus 2x. And I'm allowed to take that and substitute it into the other equation in place of the y, because it's what y equals. So I'm going to rewrite the other equation. But instead of 3 times y, I'm going to write 3 times negative 3 plus 2x. That is 3 times y. I just substituted what y equals. Plus 4x equals 14. So I'm rewriting the other equation when I make the substitution. Okay. So I think we should write that. Rewrite equation when you make the substitution. Now it gets easy, right? Step 3, I just need to solve for the equation for the remaining variable. See, now this equation, it's only got one variable in it. It's only got x's. And you guys are awesome at solving equations with one variable. I would distribute the 3, giving me negative 9 plus 6x plus 4x equals 14. I'd probably add my like terms together. Negative 9 plus 10x equals 14. Then I would add 9 to both sides, right? And get 10x equals 23. And finally, I would divide by 10 and get x equals, well, I'm going to make it a decimal, 2.3. I could leave it as a fraction. Because it's a nice decimal, I'm going to leave it as or make it a decimal. All right, now what? Last up is step 4. Step 4, I resubstitute back into the first one to solve for the other variable. So I take this and I resubstitute it back into the equation I started with. So that might look like that. That gives me the y value, negative 3 plus 4.6, and that would be 1.6. So I could write that as an ordered pair, 2.3, 1.6, or I could just write x equals 2.3, y equals 1.6. And I have solved it. So I want to review this real quickly so you're clear on what to do. Step 1 was, oops, I messed up. All right, step 1 was right here. I got the y by itself. Step 2 was when I made the substitution, right? I replaced the y with what y equals. Then step 3, I solved for x. And then step 4, that's not very good, is it? Step 4, I substituted back, once I had my x value, I substituted it back into the first equation, right? All right, that is about as hard as it gets right there when you have to do all 4 steps. Very often you do not have to. Let me go through some quick examples and we'll be done. But each of these has a little different thing about it. All right, so first of all, in example 2, a variable is already by itself, so I can just go ahead and take what that equals and substitute it into the other equation. So I'm going to rewrite the second equation, but I'm going to replace the y with what y is equal to, which is 3x from the first equation. That's the big thing right there. You learn how to do the substitution, the rest is easy. So now I solve for x. I'd add my like terms together. I would divide by 4, and I get x equals -8. I now have half of my answer, right? I have the x value. I'm going to get the y value by taking my x and substituting it into the other equation. So this would be 3 times -8, or -24. Boom. All right. Example 3. So in this equation, or in this example, both equations have the y by itself. Not to worry. Our book, when this situation happens, our book claims that this would be solved by what they call the equal values method. That is the two, well, I'll get back to that in a second. But I claim that this is just a special case of the substitution method. There's no reason to learn another method. Here's why this is the substitution method. I'm going to take what y equals in the first equation, and I'm going to substitute it into the second equation. So I'm going to rewrite the second equation, but instead of writing y equals, I'm going to make my substitution. This would be 2x plus 7 equals x minus 1. Now, our book calls this the equal values method. It says that because this is equal to y and this is equal to y, that these two amounts have equal values. So you can set them equal to each other like we did here. And that's true. They are equal to each other because they both equal y. I just don't think you need to call it a new name. It's still just substitution. All right, so now I'm on to solving. To solve this, I would subtract x from both sides, giving me x plus 7 equals -1. I would subtract 7 from both sides, and I would get x equals -8. And step 4 is to substitute that back into the first equation, where I would get y equals 2 times -8 plus 7. That is -16 plus 7. That is -9. And so my ordered pair is -8, -9. All right, I've got one more thing. Here it is. It is possible for a system to have no solutions. We know that already if you've done the first homework. That is when you graph your two lines and they're parallel to each other. That means there's no solution. Or it's possible to have, right, infinitely many solutions. That is when you graph your two lines and they turn out to be the same line right on top of each other. Every point on one line is on the other line also because they're the same line. That means there's infinitely many solutions. So what does that look like if we're not doing the graphing method? How do we know if there's no solution when we do substitution? Well, here's how. If you solve the system and you get what's called an identity, that is two numbers equal to itself, then the system has infinitely many solutions. And if you get a false statement, like 8 equals 2, that means there is no solution. Let me show you a quick example. So here, in this example, the x is by itself, so I'm going to substitute that into the other equation in place of the x. Here it is, 3.5 times, now instead of x, this is now -2y plus 4, plus 7y equals 14. See how I just rewrite the equation, but I substitute what x equals in place of the x. And now I solve it. I'm going to distribute the 3.5. 3.5 times negative 2 is negative 7y. 3.5 times 4 is 14, plus 7y equals 14. And uh-oh, look what happens. When I go to combine my like terms, I have a positive 7y and a negative 7y. Well, those guys cancel each other out. And I'm left with 14 equals 14. This is an example of the identity. It means there are infinitely many solutions. All right, last example. Again, I have what y equals in the first equation, so I'm going to substitute that into the second equation. And I'm going to rewrite the second equation. So this would be 3x minus 11. That's the y. Then I have minus 3x equals negative 13. All right, so I substituted this in for y and got that. Now I can go ahead and start solving this. I would combine my like terms, but uh-oh, 3x and negative 3x cancels out. No more variable. I'm left with negative 11 equals negative 13. Well, that is a false statement. And a false statement means that this guy has no solutions. You are now ready to solve any system of equations by substitution. Good luck. I'll see you in class.